Hello everyone, my name's Lachlan. I'm going to be taking you through the APhO 2023 Theory Question 2. So just a few things I'd quickly say. I think this is quite a hard question, it's quite technical, and hopefully by going through this as an exercise, you'll be able to develop a much better understanding of, cross products and also just doing some rotational mechanics, and you'll become more familiar and confident with that. So the first thing I'm going to do is show you guys the problem itself. Just in case you don't have access to it, I'm going to show you the Australian delegation paper, so the final Australian version of the paper. So we'll just look through each of the pages now. You can pause and screenshot as you wish. Okay, and before we get started, I'd also like to draw your attention. It's really important that you're familiar with a cross product rule, and I think it's good if you have a right hand rule that you can use to get an intuition for the directions. So the one that I like to use is I just do x cross y equals z, so you just point 1, 2, 3, it doesn't really matter which way you want to do it. One thing I will quickly point out is that we work in a right-handed coordinate system. That's the convention that we use. So if the x and y directions are defined, you must define z, so the cross product of x and y is z. There is one rule that I really want to point out to you on the paper, and that's this one here. It's a triple product rule. So that's where we have a cross b cross c is equal to the dot product between a and c multiplied by b, and the dot product between b and c multiplied by a. And I want you guys to have a really good intuition for that rule, so let's quickly talk about it together. So to better understand this rule, let's just quickly set up a coordinate system. So I'm going to set up x is going this direction, then I'm going to set up y going vertically like this. Now, z must be either going into or out of the page. You can quickly use your cross product rule, and you have that x is this way, y is that way, so therefore z must be coming out of the page. I'm going to try and draw it like this. So this is our z direction. Now let's add some vectors onto this. Let's say that we have got c is in this direction, I'm going to call b in this direction, and a is in this direction. Okay, so let's actually quickly evaluate the left-hand side where we do a cross b cross c. Well, in this case, if we do a cross b and use your right-hand rule, you'll discover that that's actually pointing in the direction of c in this case. So a cross b points in this direction. Now, if you have a look, that is now parallel with c. So that means that if we perform this, our answer is going to be 0. And if we have a look, this actually makes sense with what we've got on the right-hand side here, because we have a dot c is 0, and then we've got b dot c is 0 because they have no common component, and so therefore we're going to have 0 multiplied by b minus 0 multiplied by a, so that's just going to give us 0. So it works in this scenario. Now I'd just like to imagine what will happen if we instead make it so our a, rather than pointing directly in the y direction, actually has some component in the x direction as well. So let's do the left hand side. So a cross b cross c. So we start with a cross b. So in this case, our a cross b, if you go and do the right hand rule for this, you're going to see that you end up with some component which kind of looks like this. So when we take the cross product of this component with c, then if we use our right hand rule here, we're going to have a component coming out towards us in this case. So there will be a component which is in the same direction as b. Now if we have a look, this can make sense, because if we have a look at our equation here, a dot c is no longer 0. So that means that we should end up with some component in the b direction. However, b dot c is still 0, so that means that we won't have any in the a direction. Feel free to go back and have a quick look at that again. I just want you to have an intuition for this triple product rule, because we're going to be using it a fair bit in this problem. Okay, so now we've gone through that, let's start with the problem. So we have part 1a here. We need to express the ball's velocity in terms of capital omega, lowercase omega, r, and capital R. To help us do this, I'm going to draw two diagrams. The first diagram I'm going to draw is if we looked at the table side on. So in this case we've got the z direction coming directly out of the table. This is z. And then I'm just going to call this direction the x direction arbitrarily. So we can't actually see the y direction. In this particular case, the y direction with our current coordinates would have to be going back into the page. But I'm just going to make this a 2D diagram. Then we have our ball, might look like this, and it's rotating around. Let's just say like that. Okay, and so it's got some like little r. Now r is a scalar, but it's some distance there. Big R is, I guess, how far away we are. I won't show it on this diagram because it's not really that clear. For our omega, so our omega is, in this case, if the ball is like rolling around like this, then our omega is like going into the page. So I'm just going to represent that with the cross. that's our omega, and our velocity, in this case, if the ball's rolling this way, would be in this direction here. And so what we want to do is we want to use like a kinematic constraint to relate these two parts together. So how does V depend on omega? I think this is something that a lot of people have hopefully seen before. So in this particular case, we're going to get that V is omega cross ZR. Now let's just double check that our directions are correct. So if we apply cross product, and indeed I get the direction of V illustrated in the diagram. Now I want to draw a second diagram because we've only considered the ball rolling. What we haven't considered is the turntable moving. So if I then draw a bird's eye view, let's imagine we have this turntable turning this way. So if we have our like origin directly in the middle, then in our positive Z direction, so I'm going to call the positive Z direction coming directly out towards us, then we are going to have our capital omega, so capital omega is coming directly out towards us. I'm going to call this direction X, this direction Y. Okay, and if we have our ball, to the center of the ball we have a vector capital R, and it's got some velocity V going that way. Then we're going to have an additional component here because we have the table is rotating in addition to the ball rotating. So if we take the table's rotation into account, then we're going to have to add an extra term. So if we like update our formula, we're going to have the same as before, V equals omega cross Z direction R. But now we're going to have this additional term where we have to take our cross product between our omega and Z and R. Now if we just have a quick look at the direction, since like Z's coming out of the page and R's going out that direction, indeed we find that that gives the velocity V direction illustrated here on the diagram. So that's part 1A. Now what I'd like you to do, just to get a little bit of intuition for how this situation works before we go on, I'd like you to quickly have a look at a video of somebody who's demonstrated this really effectively. So what I'll do is I'll just put the link here and I'll put it in the description of this video. I highly recommend just give it a look so that way you can have good intuition about what's going on in the problem. A key thing to notice is that the ball will actually rotate around in the same direction as the table. So if this ball's going to like do a little bit of a circle, then the circle is going to be going in the same direction as the turn of the table. The other key thing to really notice is that the table actually spins around a lot faster than the ball rolls around. The ball, I think, yeah, it only does a fraction of the rotations compared to the table, and later in the problem you're going to see why. Okay, let's do part A2. So for part A2, they want us to use Newton's second law and a torque equation, and then they want us to find the acceleration of the ball. So to do this, let's start by just writing down, in this case we simply have that the force acting on the ball, the net force, is equal to m, and then rather than writing A, I'm going to write v dot. Okay, Newton's second law, thank you very much. Then we have a similar kind of torque or rotational equivalent, so tau going to be equal to, so in this case it's going to be I, and I'm going to write omega dot. But in this case we know that the torque acting on the ball in this case is just going to be equal to the force acting on the ball, cross product with R, and note that this is going to be in the Z direction because R is like directly up and down going from the center of the ball down to the table. So then we've got our torque there, which is nice. So note that I've kind of incorporated the minus sign by doing F cross R rather than R cross F. Okay, so this is kind of like the first part of this question. Then what we're going to do is we're going to substitute into our answer from the previous part. So I'll just put that up so we've got that for reference. Okay, our next step is we're going to have to differentiate. So to be honest, there's lots of different ways that you can go about solving this from here to find V. The way that I'm going to do it is we're going to differentiate V. So in this case we're going to get, now note that R isn't going to, small r is not going to change over time here, so that term we can just differentiate omega. Then we have that for this part of the problem capital omega is not changing, so this is just a constant. And then if we differentiate R we just get V. Okay, then our next step from here is we're going to make some substitutions. So by combining that force and torque equation we can get the following, and so then I can rearrange that to solve for omega dot. Okay, now I can substitute that into my equation in red, and I'm going to get, and from there let's remember our triple cross product rule, which was A cross B cross C, A dot C B, v dot ca like this. Okay, and we're going to apply that to this scenario here. So that first term, if we have a look, we've got v dot cross z more or less, with the factor of mr squared out the front. So in this particular case, our b dot c is going to equal to 1. So that means that our direction that we're just going to get in this particular case is A. And note, because we have unit vectors for z, that means that we're going to get just a factor of 1. That dot product is going to equal to 1. And then when we do our A dot c for the first term, the A dot c part, these two vectors are orthogonal to each other, so that means we're just going to get 0. So if you like, I'm imagining this bit goes to 0, and this bit's going to equal to 1. So let's write that. I'll start using the other side now. So at the end of all that, I just get v dot. Okay, and now what I'm going to do is bring that term to the other side and factorize it out. Sorry, please note I've made a small error. The formula has a minus sign here. I apologize. That should be a minus, which means that this gets a minus. Okay, and now if we bring this to the other side and factorize it out, we get, and then we can divide both sides by the scalar, and we get. Now the only other thing that I'll just quickly say at this point is that in the problem, they actually give us a factor alpha that we are allowed to consider, and in the problem they define alpha as this term here. So alpha equals. Now I'm just noticing that this part of the denominator here looks pretty similar. In fact, let's just rearrange that slightly. If we have a look, that we can just make that so it's all on the fraction over I, and then we get I plus mr squared. So if we have a look, this is actually like the inverse of alpha, but it's on the denominator of a fraction. So what that means is that we can just write this is v equals alpha omega z cross v. Okay, that's part A2. And before we move on to part A3, I just want to point out, if you have a look here, you see that v dot is actually at right angles to v. So that means that our acceleration is at right angles to our velocity. So when this happens, this means that we normally get circular motion. So let's just keep that in mind as we're looking through the later parts of the problem. Okay, so for part A3, what we need to do is we need to find the velocity. And so we've already found the acceleration, so I guess what we just need to do here is integrate with respect to time. So if we integrate both sides, we're going to get the following. Note, alpha and omega are constants with time, as is the z direction. Okay, and when we integrate our acceleration, we're going to get the velocity, and we're going to evaluate this at 2 points. So we're going to do what the velocity is at the current point in time minus the initial velocity. So this bit essentially just becomes v at the current time, and this bit becomes r of t. So then when we substitute in for the 2 times, we're just going to get v, which depends on time, minus v naught. Okay, so then I guess we're kind of done already, but it's kind of convenient if we rearrange this in 2 ways. So the first way I'm going to rearrange it is I'm just going to bring v naught to the other side. Then I'll also write an additional line of working where I absorb v into the brackets with r, and that'll be helpful for us later. Apologies, I missed my cross products, so I'm just putting them back in now. Now, it would have been really nice if I could actually kind of get, factor out this, this z cross, and the only way I can do it is if I kind of think about the triple product in reverse. Okay, and I'd like to get something pointing in my v naught direction. So what I can do is I can kind of just take this expression here, and then if I use my triple vector product trick, then I can see here that where I do b dot c, I'm going to get nothing. But if I do my a dot c term, that's going to be pointing in the direction of v. And z dot z hat in this case is just going to be 1. So in this case, I have this nice property where this is going to give me, in this case, v naught like this. So this means I can actually rewrite this by kind of factoring out my z cross. So I'm going to get that v is equal to this expression here. Now, it's going to be convenient for us in a minute to think about where the center that this is occurring around. What is the origin of this? And it's really handy to do that if you have something that takes the form of r minus. So what we want to do is we actually want to turn this second plus into a minus here as well. So to do that, we can just reverse the order of the v naught cross z. If we do that, then that means that we will now be like this here. So that's our part A3 done. Now A4 is where we really get to kind of think about this, so let's dive into that. Alright guys, so in A4 they want us to find a solution for the ball, the trajectory of the ball. So as we kind of discussed before, we know this is going to be a circle because we had the acceleration was at right angles to velocity, and from this equation here we can actually see that velocity is also at right angles to position. But now what we want to do is actually just get the coordinates of that trajectory. Now I'm just going to do this in Cartesian coordinates. You can do it in other coordinates if you'd like to. Let's just get started. So what I'm going to do is I'm going to break this into like x and y coordinates here. So let me just put my vector symbols back on. And I'm going to call, rather than calling it v, I'm just going to call it r dot. So I'm just going to treat this like it's a differential equation. So if I do this for the x coordinate, so because I'm taking a cross product here with respect to z, that means that my x is going to become minus y. So this means that I'm now getting the minus y component here, and then it's going to be the same for my r naught. I'm going to get the negative y component. Now for velocity, I've done this fancy trick where I've got this z cross v naught, but I could have actually just unfactored this whole thing and just had v naught. So in this case it's still going to be the x component. So okay, then we can also write down a differential equation for the motion in the y direction. When we take our cross product here, we're not going to pick up the negative sign. When you do z cross x, you don't pick up a negative factor. So okay, so this is a differential equation. Now for the moment what I want to do is I'm just going to consider a fair chunk of this constant. So all of this is just going to be some constant. I'm just going to call it d1. And all of this is just going to be some constant. I'm going to call it d2. Okay, and what I'm going to do is I'm going to start by solving the homogeneous equation. So that's where I ignore the constants. And in this case I can see that in this case if I make a substitution, so if, for example, if I was to take the derivative of the first equation and substitute in the second equation, then I would be getting that this equation here, and I can do the same thing for y as well. Okay, and this is hopefully one that everybody's seen before. The double derivative gives you some constant multiplied by a negative version of the function. So this, of course, this is going to be a sinusoidal function. Now you might be familiar with when you are in this scenario that you just take like a constant multiplied by sine theta plus a constant multiplied by cos theta. If you do that in this scenario, it so happens that things are going to be a lot more difficult for you than if you pick a different form. So we can actually just pick the form that Rx is going to be equal to, so it's going to be some constant. So in this case, it's going to be the radius of the circle. So I'm going to call it RT, and then we're going to call it cos alpha omega t plus phi. Now the reason why it's good to choose this is that it takes advantage of the fact that we already know that this is a circular motion. It's going to have a radius of RT, and what we don't know here is some phase factor phi, which is where you actually start on your circle. And then we can use this to also find y. So to do this, what we just need to do to find our y is we just need to integrate up. So we can just use this first equation. We're going to ignore the d1 part for the moment. We're going to deal with the constants in a minute. It's equal to alpha omega and then the integral of rx dt. Note, I'm actually using the second equation here. So I've integrated up the left-hand side where I had r dot y, and I've integrated up this side here where I've got alpha omega rx. Okay, then we can substitute in for rx, and then when we integrate, we're going to get, and this term just becomes 1. And what we also need to consider are there actually are some constants on the end here that I don't know yet, so I'm going to call this one plus c1. Sorry, I just realized I missed a factor of rt on our equation for ry. Okay, so we've got 4 variables to solve for here. We've got rt, the radius of the circle. We've got the phi term, which is giving us our initial phase. Then we've also got the c1 term, which is essentially giving us this initial rx, and our c2 term, which is giving us our initial ry. So let's go through and solve all of these. The best way to do it is we can find what was the velocity at times equals 0 in the x and y direction, and what is the position at time equals 0 in the x and y directions. That'll give us 4 equations that can allow us to solve for our 4 unknowns. So let's start with the initial position. We know that it's given by. Okay, and then we can do the initial position in the y-coordinate. Okay, now we can do the initial velocity in the x direction. So And initial velocity in the y direction gives us... Okay, so what I'm going to do here is I'd like to start with, I'm going to try solving for my velocity terms to be able to get the phi and the RT. So the easy way to get RT that I can see here is that I can actually just take these two equations here, I can square both sides of them and then add them together, and that's going to get rid of my sine theta and cos theta, because sine squared phi plus cos squared phi is going to be equal to 1. So in that case, I'm going to get the following. Okay, and now I just want to solve this for RT, and make a note here that v0 x squared plus v0 y squared, that's actually just the magnitude of v0, so I'm going to express it like that. Alright, and we've just found the radius of our circle, which is great. Now, to find phi, that's going to give us our initial, position in the circle. So what's our phase factor in this case? And so in order to find this, there's actually two ways we can do it, and they're going to be equivalent. I'm actually going to do it both ways because it's going to be a useful substitution for us later in the problem. So I got this equation just by substituting back into my original equation for y. I just divide both sides by alpha omega RT, and I get cos of theta equals this. Now, it so happens that another useful form of it is actually going to be where I keep RT up the other side. So I'm going to write this one here. From that, just solve the following. Okay, and I can also do a similar thing with x. It's going to give us an equivalent answer, so I won't actually solve for phi again. But what I will do is I'll just write it out so we can use the substitution. Okay guys, just to make space, I've shrunk that down. So now we can go ahead and we can find the constants C1 and C2 for Rx and Ry. So to do this, let's start with this equation here. And then what I'm going to do is I'm just going to make our substitution. So rather than writing RT, I'll just write in our expression. And from this, we can get that C1 is going to just be R0x minus V0y over alpha omega. Now, where did I get this from? I used this little trick up here. Okay, and now we can do the same for y. Okay, and so now we have C1 and C2. So finally, we can write out our equations in full. Okay, and we've written up the full trajectory there. Now, just a few key things to kind of note. RT, or the radius of the circle, is the magnitude of V0 over alpha omega, and if we wanted to, we could also find the center of the circle. So the argument I'm going to make for this is that if we have a look at our RT cos theta, RT sine theta terms, this is clearly like the component that refers to just like moving around and around cyclically, so around a center. So the remaining parts, the R0 x and the minus V0 y over alpha omega and the y component equivalents, they actually give us the center of the circle. Now, what I'd like to do is, if we just have a look at those two parts, the x-coordinate of the center is given by this, and what we can do is we can actually just kind of factorize that to get back into a vector form. So if we're asking where is the center of this circle, well, if we have a look, we essentially can just see that one of the components here, this just corresponds to R0 vector itself, and then we have our velocity term. Now with the velocity term, we can't just write this straight away, because if you have a look, we've got the y term paired up with the x term here, and the x term of velocity paired up with the y term of position. So what we can do though is if we take the cross product between z and v, then this will give us the correct coordinates that we want. So what we actually just have to do here is add that term there. And so now we also have an equation for the position of the center of that circle. So that's part A4. Now we get to do A5. Okay, so now we're going to do part A5, and for this bit here, what we want to do is we want to figure out how long does it take the ball to return to the same spot on the turntable. Now note, this isn't the same spot from the labs frame point of view, this is the same spot from the turntable's point of view. So if we just quickly draw a diagram to explain this one, then if we imagine this is like our turntable, and then let's suppose that our ball is doing a little bit of like a circle around like this. There's one extra factor that we just need to consider here, and that's if this is like the center of the table here, distance to there, so that's essentially if that was our initial position, R0, then that needs to have the same magnitude as the center of the circle, RT. And if we have the turntable going around this way, we also have the ball going around this way. And what will happen is the ball will be doing like revolutions going around. That has a frequency or an angular frequency of omega. And then the turntable will be doing revolutions that have a frequency of capital omega. Now, if the ball just does a revolution on the spot, or if it does one complete revolution, then that doesn't actually guarantee that it'll be the same spot as on the turntable. Even though it'll be in the same position relative to the lab, it won't necessarily be the same position with respect to the turntable. So what we actually need is we need these two to essentially line up together. So in order to do that, I guess we need to figure out how are these two periods related to one another. So to do that, from our previous equation, we actually got the angular frequency of the ball's omega. So how quickly it's going around in its circles is given by, we had alpha capital omega. Then we can just substitute in for alpha, and we actually have been given the value for the moment of inertia, I. And so if we do this, what we can get is, nice, so little omega is equal to 2/7 of the big omega. So what that means is for every 7 rotations that the turntable does, the ball should do 2 rotations. What that means is if we just do 7 rotations of the big table, we'll actually know that the ball has done 2 small rotations of its cycle. That actually guarantees that it will be back at the same position in the lab frame, but also exactly the same position on the turntable because they've both returned to their initial positions. So what that means is we just need 7 complete turns, and so the time for that is just going to be 7 multiplied by 2 pi, because that's the number of radians for a full rotation. And we just divide that by the angular frequency, because the faster you're moving, the less time it'll take to do that. And so we get 14 pi over omega is the time to return. Okay, but it so happens there is a special case where we can actually get a different amount of time for the ball to get to the same place on the turntable. The key thing is it doesn't also have to be the same position in the lab. So if we do this, I need to redraw my diagram. Now imagine the ball started in a position like this one here. Then what we could actually have is that this ball could move around this small angle here. In the meantime, the table can actually do a full rotation around like that here. And it's possible that these 2 points could join up again. Now, a key thing that we just need to consider here is that we actually know that this distance here is going to be the same as that distance in there. So we can call that RT, and that's actually going to be the same as this radius in here. And so the time that it takes the table to do this larger angle around the outside could actually be the same amount of time it takes the ball to do this smaller angle here on the inside. So the key part of this diagram that I think that we need to look at is we actually just need to consider the triangles here. So if you like, we're going from some position to another position. So I can draw a straight line going across like that. And then I can actually just kind of divide this into a triangle here that looks like this, and we can divide that one into a triangle that looks like this here. So if I draw those 2 triangles slightly larger, now the key thing is that we actually have to have the distance traveled horizontally in these 2 triangles is the same for to end up in the same position. So this is going to be RT, this is going to be RT, and this horizontal distance here, I guess this is the horizontal distance traveled by the table. So what I'm just going to do is I guess I'm just going to call this X table. It's going to have to equal this distance here, X ball. We're just going to call this angle in here over 2, because that's half the angle that the ball has done if it was going to go around this trajectory here. Now, if we say that there's some angle that the table has done going around, that's actually going to be quite a large angle. And then what we're subtracting off here is essentially 2 pi minus that angle. So what that means is that this little angle in here is going to be 2 pi minus our little angle all divided by 2. Now keep in mind phi here is actually a big angle. It's going all the way around this outside bit here. Theta is a much smaller angle. It's the angle that you do going around this little bit here. Okay, and because these 2 lengths actually have to be the same, and we have our RTs are essentially the same here, we can write down a nice relationship. Just one thing I'll point out is that this triangle only makes up half the horizontal distance. I'm just going to draw in green here. Going from here to there, that's only half that distance. So if we multiply that by 2, then we're going to have 2 multiplied by x of the ball is equal to 2 multiplied by x of the table. Now we can use our angle here. So if we have a look at this x ball here, that's just going to be RT multiplied by the sine of theta over 2. And that's going to be equal to 2 multiplied by RT sine minus phi over 2. All right, and we can do some cancelling. This cancels with that. And then what's inside those brackets must actually be the same. So theta over 2 equals 2 pi minus phi over 2. Those 2's are going to cancel for us, which is nice. Now, we just need to be able to relate theta to phi. But we can do that because we know that the ratio of the angular velocities for how they're moving. From our previous part, we already know that our omega is equal to 2 over 7 capital omega. And so theta, that like angle that's been traveled, that's just going to be equal to omega t, small omega t. That's going to be equal to 2 pi minus capital omega t. And now we can solve for this in terms of capital omega. So first I'm going to substitute in for small omega, and therefore t equals 14 pi over 9 capital omega. And so what we found is that the amount of time it takes is significantly smaller if you just so happen to arrive via this coincidence. Okay, let's move on to part B of the question. Part B is similar to part A, except there's a key difference. For part B, the table is allowed to move freely rather than being forced to move at a constant angular velocity. So if we think about what does that mean in terms of diagram, well, if this is the turntable, and it's spinning around like this with some angular velocity omega, omega is no longer a constant. Omega is allowed to change over time. In part B, we just need to find the velocity and the acceleration of the ball again. And to do this, we're going to borrow some of the equations that we actually used when we were solving part A. So we've got the force on the ball, it's given by this equation here. We've got the torque on the ball, it's given by this one here. And we're going to use the no-slip condition. Let's start with the torque equation. And then what we're going to do is we're actually going to integrate both sides of that with respect to time. So when we do that, we get something that looks like this. Okay, and noting that most of the things are constants, then what we actually get is this. Okay, and then what I'm going to do is just divide I through to the other side. And then I'm actually going to take the cross product of everything with respect to z and move omega naught to the other side. And for this term over here, the final term with the v minus v naught, we're going to use our triple cross product rule, and that's actually going to get rid of our z's, which is kind of handy. So let's do it. Okay, and now we're going to substitute this into our no-slip condition, because if you have a look, we actually have that this part here is the same as this here. So that means that we're going to get, and then we can do the same thing, except we can actually have it the no-slip condition when we have v is equal to v naught, or at time equals 0. So that's going to mean that capital omega is omega naught, capital R is capital R naught, and omega is omega naught. So that'll give us. Okay, now I want to rearrange that for the omega naught cross ZR term, and that will give me. Okay, and now if I have a look at this line here, I'm going to solve that for V, and I'm going to make a substitution for omega naught at the same time. Apologies, I missed omega naught should be crossed with Z. Alright, so I'm going to bring all my V terms to the left side. On my left hand side, and then on my right hand side, I'm going to get. Okay, and then if we actually remember, we were given a nice definition for a shortcut term we can use called alpha. So in this case, we can see that our v's are actually multiplied by 1 over alpha. So, and if we gather our v naught terms, then we'll actually see that this is also equivalent to 1 over alpha. So that means that what I've got here is now, and then if we just multiply everything by alpha, then we have our expression for v. Okay, and then we can just differentiate that with respect to time, and we can get our acceleration. So this isn't actually too bad. So please note that when we differentiate, the omega naught, r naught, and v naughts are all going to go away. So that means that we are just left with a product rule to do for this term here. So take the derivative of the first term, and then take the derivative of the second term. Okay, and if we wanted to solve for acceleration and we didn't want it in terms of v, we could actually do a substitution here for the top line into the second line. Alright, and that's part B1 finished. Alright, so now that we've found the acceleration of the ball, we can actually use this to figure out how is this disk going to accelerate underneath the ball. And so the trick for this bit is we just want to look at what are the torques acting on this disk, and the torque on the disk is going to be essentially the negative of the torque on the ball. So if we write an expression for the torque on the disk, we're going to have, so the moment of inertia times the angular acceleration, which is in the z direction, just going to be equal to minus r cross f, where in this case f is m times the acceleration of the ball. The reason we've got this minus sign is that it's going to be like the disk is going to receive the opposite torque that the ball receives, so it's like an equal and opposite torque in this case. Okay, now the issue is here that they don't want us to use v or v dot in our final answer, so we're going to have to do some substitutions to get rid of this. So in the previous part we had expressions for v dot and v. I'll just quickly write those down for us. Okay, and first thing I'm going to do is we're going to substitute in for v dot, or for the acceleration, which gives us... Okay, and now we're going to use our triple product rule, and when we're using the triple product rule, what we're going to do is we're going to use these two identities here. So we're going to have r dot r just essentially equals a scalar r squared, and r dot z is going to equal 0, because z is pointing up and r is strictly horizontal. So then if we apply this triple product rule, we're going to get... Okay, and now we need to get rid of v, so we can substitute in our expression that we have for v, and we get... So just a quick note, because everything's in terms of z hat here, I can just get rid of that, which is nice. Okay, so now I've got that, let's keep going. So now everything's scalar. I'm just going to bring this first term to the other side, and just keep in mind all of this bit here is just r dot v. We're going to use that trick a little bit later. Now if we want to, we can do a little bit of a simplification here using our triple product rule. Because we've got r dot and then you've got z cross r here, well z cross r is strictly orthogonal to r, and then r dot something orthogonal to r is going to be 0. So that means that we can actually just get rid of this term in here. Alright, now we'll just write this out with a little bit of factorization. Okay, now they actually told us that there's this symbol delta that they'd like us to use, where delta is given by id over mr squared. So to be able to use that, what we're going to have to do is divide everything by mr squared. So let's do that. So this bit here is just going to become our delta. And sorry, I actually dropped these m alphas here. Apologies, I'll go back and fill those in, which means that these minuses are in the wrong places. Now let's cancel out the n's. Okay, and then we just have to divide both sides by this expression here, which will give us... I know that I've missed r dot here, so if you like, this has just got an r dot on the end. And what I'd just like to point out, because this is going to be important for our next part, that if I just highlight this bit in green, this bit here, this was actually all equivalent to v dot r. So we might use that when we're solving B3. Alrighty, so that's our B2 done. Let's move on to B3. Alrighty, for B3 we're going to need our result from B2, so I've just saved it on the right hand corner over here. Now essentially all we need to do is integrate this function with respect to time. However, there is one extra constraint they've put in the problem. They're not allowing us to have things in terms of v0. So first of all we're going to have to find a way to eliminate our v0. Now in order to do that we can do a little trick. So you might remember that everything that I've got here we decided that's underlined in green was equivalent to v dot r. Now, if we think about v dot r and we want to eliminate v so there's no v in it, there is this kind of trick that we can do. So let's imagine for a minute that we're going to take the derivative d dt of r dot r. So if we use the product rule here, then we're just going to get that this is v dot r. Now this is handy because the r dot r is essentially just a scalar. This is something that we can, and also it's a variable that we're allowed to have in our answer, which is really nice. So what we can then do is, if we just like divide both sides by 2, then we can get rid of this bit that's highlighted in green by essentially using that v dot r is going to be equal to a half dr squared dt. So we can substitute this in, and then we get this. Alright, I'm just going to do the denominator first, like this. Now, integrating the right hand side here is going to be a little bit difficult. Now, it just so happens though that if you look carefully, there's a little trick that we can do here. If we were to take this omega here and bring it to the other side, then we can actually write this like this, where we have the derivative of the function on top of the function itself. So that's really handy. Now I'm also just going to be a little bit careful in the way that I arrange this here, because if I just bring this minus 1 over 2 out the front, then let's have a look at this denominator. And now if I compare that very carefully with the numerator, it's actually going to look like this. And if you have a look, what we've actually got here is that this numerator is actually the time derivative of this denominator, because the only factor that depends on time is capital R. So what that means is when I integrate this, I'm going to have this nice relationship where the derivative of the bottom is on the top, which means that I can just simplify that to a log. So let's take the integral, time equals 0 to time equals t. Just to make this easier, I'm going to multiply the top and bottom by r squared. So if I do that, this goes away, and I get an r squared here. Alright, and now let's substitute this in. So on this side here, we're just going to get the log of this, and then we have to subtract off when it's equal to 0, like at time equals 0, so subtract off omega naught. And then here I've got minus 1/2. Okay, and now I'm going to use my log laws to get, and cancel the logs on both sides as well. So that minus 1/2 is just going to become a square root, and I'm going to flip these, so I'm going to have, okay, and then I can just multiply my omega naught to the other side, and I therefore get, okay, that's looking pretty good. I'd say that's our answer for B3 done. Now for B4, what they just want us to do is find the maximum possible value for omega. Now there's essentially only one variable here, and that's r squared that we can see here. So if we just set r squared equal to 0, that's going to give us the maximum possible value for omega. So if we just put that in its own little box here, and this value is going to occur at r equals 0, and the larger the r naught value was to start with, the larger this is going to be. And that kind of makes sense, because if the ball came from a really long way out and then kind of rolled in, then you can pick up more angular momentum as that ball moves in from further. Alright, and that's B3 and B4 done. Before we have a look at B5, it's going to be important that we just revise something called conics. So we'll just quickly go through that now. Alrighty guys, so before we move on to part B5, I thought that I would just talk to you about something that's going to be important for us to understand to be able to do this, and that is conics. Now conics is called conics because it's about looking at the cross sections of cones when you cut them at different angles. I'm not too worried about thinking about it in terms of cones. What's most important is that for you guys, I just want you to know that if you have an equation that takes the form of what you can see here, so I've just called up a website called Desmos, which is great for visualizing different functions. So if you have a look here, we've got ax squared plus bxy plus cy squared plus dx plus ey plus f. So this is the general equation for conics. And I've set f is equal to minus 10 for us, so we can just imagine we've got everything else on this left side equal to 10. And it so happens, depending on what parameters you put in for a, b, c, d, and e, you can get different shapes. And if you have, I've set everything to 0 except for a and c at the moment, and f of course, then you get a circle. Now if you play with d and e in this scenario, all that happens is you translate your circle. You do also increase the size of it, but the way that I just like to think of it in this case is that these parameters are primarily responsible for translations, and e is for vertical. A, B, and C are actually what are required for changing the shape. Now if we have a look here, so we start with an ellipse. I'm just going to get C to scroll through some values. So here if we have C change, then first it becomes an ellipse. So if we have a look, we're back at our elliptical stage, so circle to ellipse, and then it will spread out to become a parabola before becoming a hyperbola. And so for different values of C, in this case, you're going to get different types of functions. And it's similar with A, it's just changing in the x direction rather than the y direction. Now an important other term to think about here is you could think about, well, what's going to happen if we change B? And the answer is, maybe just to make it clear, I'll make it so we start not already on a hyperbola. So B essentially rotates your shape around. Okay, so those are our different parameters in a conic equation, and then what I want to show you now is a rule. I've copied this straight off Wikipedia, but this is essentially telling us the rules for when you get different types of shapes. So I'm not too worried about the matrix part at the top there. Don't worry too much about the determinant, but instead have a look at these rules that are in this bit here. So it so happens that if you have b squared minus 4ac is smaller than 0, then you're going to get an ellipse. Now you have a very special case. If a equals c and b equals 0, then you get a circle. Then we'll get a parabola when we have b squared minus 4ac equals 0. And if b squared is greater than 4ac, then you get a hyperbola. Okay, so this is the basics of conics I just wanted you to know before we go and explore part B5. Let's do that now. Okay, so part B5 is quite a long question with quite a few subparts. I've got it up on the screen here. What I want to do is just break this down and do it part by part. So the first bit they want us to do is they want us to find the angular momentum for the system, and they want us to find the part of the angular momentum that can change over time, so ignore any kind of constant components. So let's start by doing that. Let's write an expression for the angular momentum. So in this case, we're only considering the z direction of angular momentum, and we're going to call the total angular momentum mz. This is in the z direction. Now this has got contributions from two places. One, a contribution from the table, rotating, so that's just going to be given by the moment of inertia of the table, multiplied by the angular velocity of the table, and that's in the z direction. And then you've got the ball. Now for the ball there's two components. There's the fact that the ball actually moves around on the table itself, and that could be contributing to the total angular momentum. Then you also have the fact that the ball could be rotating around like this. Now, this isn't exactly what we expect. We expect it to be kind of more rolling, but if it is rotating around, then it will have a component around like that, so we've got to add that on too. So first, let's use the position of the ball. So that's just going to be r cross p. So in this case, p is just going to be mv. And then we also have to add the component due to the ball potentially spinning about on its axis. Now this final kind of component that we've got here, there's no way that you can actually change that rotation speed, at least in the frictionless case, because there's no way to apply torque to the ball. If you have the ball like spinning around like this, then the only way to apply torque to that is to have an off-center torque to that, but the only contact point is at the bottom of the table, directly below the center of mass, so there's actually no way to adjust that component of the angular momentum. So that means that when they're looking for the part that I guess can change, that isn't going to be conserved over time, then we're looking at our we can get rid of that final term. So our L dot z, when I say dot z I just mean L in the z direction, is given by that. Now, just one thing I'd like to point out here, we don't actually need this for later on in the question, but it's just good to have in mind that later in the problem we're going to use L as a constant, and you might think, oh, why is it that we can just have L as a constant? Well, because this is conserved, it's also initial to the original conditions. So we could also just write that this L in this case is equal to this constant here, okay? So that means that now we kind of have permission to use L as a variable going forward. Now, the next part that they want us to do is they want us to refer to our answer in B1, and then they want us to write velocity in terms of c, where c is the part of the velocity term that does not depend on the position of the ball. So let's just rewrite what we had in B1. So we had v equals, okay, this term here, and clearly the only part that depends on the r is this first part here, so the rest of that is going to be c. So I guess therefore we have our c's like that, and that means that I could write v a lot more compactly now, like this, and we can actually substitute this into our expression for L. Alright, and now what I'm going to do is factor out all of the terms that have got capital omega in them. Okay, now what I'd like to do is actually solve for omega. That's the whole point of this question, and what I'd like to do is kind of make it so I'm not dealing with a vector anymore, I'm just dealing with scalars. So I'm going to take the dot product of all these terms with respect to z, and then I'm going to use the triple product rule for my r cross z cross r, which is going to give me a factor of r squared in the z direction. Alright, so if we do all that, we're going to get, and just to clarify, r squared is like r dot r in this case. Alright, now the next thing they tell us to do is to line up the x-axis with C. So what this means is we can actually get some information about how R cross C is going to work. So in particular, what we can say is that we know that we could write R in general as x hat plus y hat. Now, if C is directly in line with the x direction, then when we take the cross product with R, then the x component's going to go away because they're not orthogonal, they're directly in line. So that means we're just going to get that y component, and then what we're going to have is we're going to have the y component of R crossed with x component of C. And when you take y cross x, or y direction cross x direction, you get minus z. So that's going to give us a minus sign here. So let's substitute that in. Sorry, I forgot to write that I was taking the dot product with z before. So, alright, so I have the y component of R left over, then I'm just going to call C without the vector symbol, the magnitude of C, and that's all going to be in the z direction. Alright, and they prefer it if I use the symbol delta rather than ID in this case, so what I can do is I can just divide everything by m and also factor in an R squared, so that'll look like L over m plus yc delta. I need this R squared term. Okay. Alright, so now what they want us to do is combine this with our answer from B3 to eliminate omega, and that way we can find the trajectory of the ball. So, first thing we're going to need is our equation from B3, so let's write that in. I'm just going to multiply everything by R squared to make it simpler. Okay, and I can set that this omega squared in here is going to be equal to this expression for omega, which means that I'm going to get... Okay, and then the two denominators here are actually equal to one another, except this one on the left-hand side is squared. So I'm going to multiply the square of that up to the other side, and then I'm going to square this left-hand side over here as well. Okay, now at this stage, we just want to simplify some stuff out so we don't have to write out so much each time. So what we're going to do is we're going to call this entire chunk here, I'm just going to call K. Now, this L over M, I'm just going to call lambda. And then I also just want to note that since we've got R is x hat plus y hat, then R squared is just the dot product of R with itself, so that's just x squared plus y squared. Great, and then we can just substitute all of that in and expand it out, and we're going to get... Alright, and what I want to do now is just rearrange this so it kind of matches my conics formula. So it looks like a x squared bxy plus c y squared plus d x plus e y equals minus f. Where we actually want minus f to be positive. Alright, so let's do this. So, for my x squared terms, I've got alpha k x squared. For the xy, I've got nothing. Okay, for y squared, I've got k alpha minus c squared, y squared. Dx, I've got nothing. For just the y, I've got 2 lambda cy, and that leaves me with lambda squared minus k r squared delta as my f term. If you recall everything that we were saying about conics before, essentially if we have a look, the parameters that are going to determine what our shape is here is, okay, b, but that's 0, so that's not interesting. Then we've got a. Now I'd just like to point out at this point, if you're looking on for the official solutions, I actually have something slightly different. They have an extra factor of alpha with their a, like they have an extra factor of alpha just here, and they've got an extra factor of alpha with the k and y squared. Now I cannot see how they got that, so I believe what I've written is correct, but if somebody thinks that I'm wrong, please let me know and I'm happy to go back and change this. So I have a equals k alpha, and I have c equals k alpha minus c squared. Now the key factor that we needed for this to work is we always looked at for AC and how it relates to b squared. So in this particular case, if we have AC is greater than or equal to 0, well actually if you have a look at A, K is strictly positive and alpha is strictly positive. So only C can be negative. So really C is the determining factor here for whether or not for the different shapes we get. So if we have AC is greater than 0, then we'll get an ellipse. But this is strictly K alpha greater than C squared. Alright, if we have AC equal to 0, then we get a parabola. And this is going to be K alpha equals C squared. And then if we have AC smaller than 0, we get a hyperbola, which means that K alpha is smaller than C squared. Alright, and that's part B done. Now we just got to do part C. Alright everyone, let's do part C1. So, for this question, they're asking us, so they've given us a new situation now where there's a magnetic field around the ball. So I might just draw a diagram for us on this side over here. So imagine we've got the ball like this, then we've got a magnetic field coming up like this, call that B, and it's in the Z direction. Okay, and then at some other angle we're going to have omega. I'm not going to make any assumptions about what direction omega is. I'm just going to imagine it's going around this way. Okay, and we've got charge along the outside of the ball now, so it's going to experience forces and torques. So what I'm just going to do is I'm going to take a random point, or I might not make it so random. Let's pick this point here, so this omega is meant to pass through the middle of the ball. Sorry, so just a sec, I'll make it in line with that. We're going to like have to integrate over the surface of this ball in a minute. So I'm just anticipating and I'm setting up that this is my theta direction coming down from the vertical. The radius here that we've got is little r. Vector r is this vector pointing this way. So that's going to be our vector r, and it's going to change direction depending on which part of the ball we're looking at. Alright, let's maybe go from there. So let's just start by writing a few equations. So we normally have like F equals ma, so in this case I'm going to start with our force equation, m, and I'm just going to call it v dot, going to equal, okay, so we've got like a friction force from the bottom, so in that case that's just going to be, I'll call it friction force, or floor force, I don't mind what you call it, and then we're also going to have a magnetic force, so the magnetic force is given by QV cross B. Alright, so that's a force equation. Now let's do a torque equation. So for a torque equation, I can do... Okay, and tau S that I've got on the end here, this is like the torque that we have due to the fact that we've got charge moving in the magnetic field. So we're going to have to like take that magnetic force and we're going to have to like figure out all the points where it's acting on the ball, and we're going to integrate that up to get tau S. So let's give this a go. Just before we do, there's a couple of things that I thought I'd point out. So if we imagine that we've got this little point just here on the diagram, and we're asking where's the velocity, well we can see that like if this ball's rotating this way, that this part of the ball, like our V in this case, is going to be coming out towards us. So V of this part of the ball is coming here. I guess I'll just call that Vs. And then we have this relationship here that Vs equals omega cross r vector. Okay, so if I have this, let's just deal with the magnetic component of the force. So I'm going to call the magnetic component of the force Fm. Let's imagine I have some small part of that, so dFm. So the magnetic force, let's say due to this little point here, that's going to be dq Vs cross B. And if we think about what direction is this going to be on our diagram here, this is kind of interesting. So we've got our B pointing up and we've got our V out of the page. So when I do that, I get the force is actually in this direction here. That's actually not going to be that interesting for us here. Like that's just like kind of pulling outwards. But if we were to consider another point, like this bit at the top here, so this is also having the velocity come out towards us. In this case, the force is still in this direction here. But the torque, then, if we do r cross F, is going to be coming out towards us. So the torque's actually in the same direction as the velocity at the top here. Now, if we were to consider the bottom, what's going on here? Well, now I've got the velocity is going into the page like that. That means that our force is going to be going this direction. But if we consider our torque is still coming out of the page when we do that r cross F, because r is down now. So the torques won't cancel out to 0. We can see the one at the top and the bottom here are summing up positively, and then the ones that are along the equator here are going to be like 0. So anyway, we'll take this into account more formally when we do our integration. We've got our force here. Let's write down an expression for that torque. So our d, like surface torque I guess you call it, is equal to the r vector cross dfm r cross. Now we've got our so I'm just going to put the dq on the end for the, in a minute. So here I've got my v, but I know that my v is like omega cross r, so I can do omega cross r, and then that all has to be crossed by b, which is bz dq. Okay, now what I'm going to do here is we're going to have to simplify this. So we're doing kind of like a 3 vector product here. So I'm just going to call these vectors A, I'm going to call this cross product in the middle here B, and I'm going to call this bit here C. Now, what we're going to do is we're going to use a slightly different version of the triple like cross product rule. So this one is when you have the final 2 terms get multiplied first. Now I see why I needed my bracket, because this R cross all of F, that bracket has to go there. And which vector product you do first is actually important here, so we have to get the order correct. So now, rather than doing A cross B all in brackets cross C, now we're doing A cross B, C in brackets. So let's do that. So I'm going to write the rule for you in red down the bottom. Let's just break this down. So if we still do D tau S, then we're going to get, so first thing I'd like to point out is A dot B here is strictly going to be 0 because omega cross R is at right angles to R. So that means the second term is going to go away, so we're just going to have a first term here. And so the first term is A dot C, R dot B, and then we're going to still have our cross product there. So, alright, now I want to integrate this up so I can figure out the total torque. So to do that I have to integrate over the whole area, so that means that tau S is going to be equal to, I'm integrating. So in this case I'm going to do from 2 pi to 0 d phi. Now when you do that you pick up a factor of r sine theta, because the distance d phi that you do going around like the equator, our like longitude coordinate, how far you travel depends on the radius, and it depends on whether you're near the North Pole, South Pole, or near the equator. So then we're also going to integrate over theta, and we've got to go from the top to the bottom. So we're going from pi to 0, and that's d theta. Now just from those two, for theta we also have to take into a factor of r. So just from those two we actually get r sine theta straight up. We've got to integrate essentially over the area. So to get this dq here, essentially it's the area, so this d phi and this d theta multiplied by a charge density I'm going to call sigma. And then of course we've still got our terms from before where we have r dot b and the cross product between omega and r. Now for r dot b here, the angle between r and b is not a constant, it changes with time, but it is equal to the cos of theta. So if you have a look at our diagram over here, b is pointing up, r, the angle here is this cos, so when, and it's separated by this angle in here, so we can see that these are going to perfectly line up when you have theta equals 0, so that's why we're using cos in this case. So if we've got, now it's just going to be the magnitude of r times the magnitude of b, so I've taken away the vector symbols, cos theta, and then we still have omega cross r. Okay. Now, let's have a look. What are our constants? Sigma's a constant. R is actually a constant here. Like, that's just the radius, so that's fine as long as it's not vector r. Sine theta's not a constant. Cos theta's not a constant. Omega is actually a constant for this integration, so we can pull that out the front. Okay, and then we can do our integral from there. Okay, so let's pull all those constants out the front, and let's substitute in r into our x, y, z coordinates. Alright, now if I think about what is the r vector here, well it's got an x coordinate, a y coordinate, and a z coordinate. What's the x coordinate given by? Well, I haven't exactly decided like to find exactly where azimuthal angle is going to be, or my latitude angle is going to be. I don't really care if we set it to sine or cos, it's all going to cancel out, but what is important is that the magnitude of the x coordinate here is going to depend on sine theta. So let's just call this one cos phi for the x coordinate, which then means that my y-coordinate is going to be given by sine theta sine of phi. Alright, I'm just going to change colour so I can keep writing over the top of my diagram. That's a y. Plus, in this case, I'm going to have cos theta z. These x and y components are going to go to 0. let's explain that in two ways. First of all, I'm going to integrate from 0 to 2 pi of cos phi and sin phi independently. That's clearly going to be 0, and anything multiplied by 0 is 0, so they're going to go away. That's a mathematical argument. For an intuitive argument, do you remember how we were trying to figure out what was the direction of the torque? And if we had a look, the force is going outwards when you're on the equator here, and that means F dot R is going to equal 0. So really, I only care about the points like where I have Z components of R. The X and Y is just going to cancel out because that F cross R is going to be 0 when they're in the same direction. So I don't mind if you want the mathematical or the intuitive method, whatever works for you. But what that does mean now is I can simplify this down a bit. So I'm only dealing with the Z coordinate. So let's do that. Okay, now doing the integral over phi is super easy. That's just going to give me a factor of 2 pi. Doing the integral of sine and cos here, not quite as easy. But what I can actually notice here is that sine, or minus sine, is the derivative of cos. So that actually means that if I was to think about the expression, I'll just write it in the middle of the board over here, cos cubed theta, and I was going to take the derivative of that with respect to theta, then I would actually get minus sine phi cos squared phi, and I'd get a factor of 3 at the front. So I can kind of use this in reverse to be able to integrate this thing here. So what that means is I'm going to get so from my phi's I get my factor of 2 pi, r cubed sigma b omega cross, in this case, sorry I dropped my z. This is all in the z direction. Omega cross z. Alright, and then I have minus 1 over 3 cos cubed theta, and I have to evaluate that at pi and 0. Now when I do this, cos of pi is minus 1 and cos of 0 is 1, so that means that I'm going to essentially get a factor of minus 2. So I do minus 1, and I get a factor of minus 2. So if I put that all together, I already had 2 pi, now I'm multiplying by 2, I'm cancelling out my minus that I've got there, so that means I've got 4 pi. Okay, and then this is all going to be divided by 3. Then I've got r cubed b, and then I've got omega cross z. Okay, now this is looking like it's starting to get pretty close. However, what I haven't done now is I haven't taken into account that when I did this substitution that you need a factor of r. So there should be like an r here, and an r in front of that. And so that means that I should have actually r to the power of 4 here, and r to the power of 4 here. Apologies for the mistake. And then, notice, because I had like sigma as my charge density, but the total charge, which I guess I'll just call Q, is going to be equal to the charge density multiplied by the surface area of the sphere, which is 4 pi r squared. So in this particular case, I can just like make that substitution back for Q to get my answer of Q r squared sigma b omega cross z. Okay, now that I've found that tau s, I've actually got everything they asked for in the question. We've got our Newton's second law at the top, then we've got our expression for the torque, and then we've managed to find the torque due to spinning around its axis in the magnetic field. So let's move on to part C2. Okay, so for C2, I've included the question here, but if you have a look, I've also included the first half of C3. The reason is because in C2 they tell you that they want the acceleration of the ball in terms of these variables here, but then if you have a look at C3, they're actually assuming that you've gone further than that and gotten rid of your omega values. Otherwise you couldn't have it in this form here. So that way, because we've got that C3 there, we actually know what we're aiming for. They're not happy for us to have our variable in terms of omega. Okay, and that just is letting us know what we need to do. Okay, so they're kind of nice that they are telling us to use the results of C1. So from that, we've got our like force formula, which we can actually rearrange to get the friction force. Alright, then we also have our torque law, which is... Okay, and then what we haven't considered is we actually also have our no-slip conditions as well. So let's just have a look at those. So the first no-slip condition can just be for the velocity. So we have... Okay, and then from this, what I can actually do is just rearrange this for omega. To get omega by itself, or omega r by itself, what I'm going to do is take the cross product with z, so take a cross product of everything with z. Then I'm going to have my nice trick where if I have like z cross something, then I'm going to have those z hats cancel out, which leaves me with, okay, then I also need to take the acceleration no-slip condition, and then I can actually now do my same trick where I take the cross product of everything with r, and that means that I'm going to get, sorry, I just missed a dot on my torque equation there. And then I'm just going to rearrange that again to get, okay, so first step I'm going to take this and substitute into my torque equation, which will give me, and I'm going to substitute in for F. Okay, and if I take stock of this is pretty good. All we've got to do is a little bit more rearrangement and then we'll get there. So the next thing I'm going to do is just going to take the cross product of everything with r z hat. That's going to get rid of some of these z terms on my v dot terms, and it's also going to mean that I can just get rid of this r and that pesky fraction there. And when I do that, I'm going to get, so let's just bring this other v dot term to the other side. Sorry guys, I just realized that there is an error here. I've done this here, this r cross f, but r, this is for the friction force, so rather than it being an r vector like that, should actually be a scalar r multiplied by z hat. Apologies. So that means that this r is actually, and that's why my I can do this trick to get my v dots, because when I do this cross product here, this z cross v cross z, that's going to cancel out my z's and I'm just going to get my v. Alright, and I had to bring this I omega v term to the other side, so that's minus, and now I'm going to have plus qr squared from this term here, and that'll be v cross b. And sorry, I took the triple product, so that z's gone away. Now, for this part here, I want to get rid of this omega, but luckily I've got this expression that I can use here. So if I substitute that in, then I'm actually going to lose the r, the factor of r that I'm multiplying up. But what that means is that I should get the following instead. And that's all crossed with z. And that's all crossed with b, which is in the z direction. And that's all going to be crossed with z. Alright, so let's just play with this last term here, because we've got a lot of cross products to get rid of. So if we first look at this v term, so we're essentially doing v cross z and then crossed with z. So that means that we're just going to get this factor of b as a constant, and we're going to get a vector pointing in the direction of v, and then we still have to take the cross product with that z. But that's okay, we can deal with that. Now for this other one, we've got r, we're crossing with z first, then we're crossing with z again. So that's going to be nice and simple, we're just going to be left with that factor of r. So let's write it out. Oops, and I forgot to cross this one with z, apologies. Notice that I pick that minus sign up when I do my triple product rule, and so that's why this minus has become a plus here. Alright, then I can notice that this term here, b q r squared v cross z, actually matches the qb r squared over 3 v cross z. So I can just add those terms together, which is nice, which means that I'll be left with, and this one also picks up a minus sign from the triple product. Okay, and if we have a look at our equation, that essentially matches the form that they've got for us at the top here. The only difference is that we could just move all the terms to one side, so that way we get equals to 0. And so if we do that, what that means is that we're going to have, in this particular case, that beta is going to be equal to, and gamma is going to be, okay, and that's C2 done, so now we're all ready to start doing C3. Okay, so I've just included the second half of B3 on the screen here because we've actually already done the first part. And so I've just got our constants beta and gamma on the right hand side of the screen here. It so happens that we won't be using those for a while. But what we do need to do is actually take the differential equations, so they're of this form, and then we need to convert these to polar coordinates. And so they've given us this transform here that we can use to convert from x and y into rho and beta. What we do need to do though to be able to do that is figure out what x dot and y dot are. So let's do that now. So let's start with doing x dot. So all we're going to have to do here is just differentiate, and we're going to use the product rule, and we're going to get, I'm not going to show the t dependence here. So that's our first term. Then for the second term we have to use the chain rule. Okay, now let's do y. It's very similar. Okay, and I'm just putting some brackets there so that way we know what's inside the sign and what's not. Okay, now it's going to be harder, but we just have to do the same thing again to get x double dot and y double dot. So let's do that. Okay, so that's from taking the derivative of rho for the first term. Now we also have to take the derivative of that cos, so we're going to get... Now, when I go to take the derivative of this next part of x, see how it's got rho sine eta, then eta dot. So this rho term, when I take the derivative of that, I'm actually going to get back the expression I've just written down. So I'm going to get 2 of those, so I'll just put a 2 there. Okay, so then I can keep the rho constant and then take the derivative of the sine term, in which case I'm going to get, so in this case I pick up an extra factor of eta dot, and then now because it's actually got this eta dot on the end, I also have to take the derivative of that and hold the rho and the sine constant. So that means I'm going to get like that. Now you can do the same thing for y. No, this is actually the same as above, I just put the eta dot in front rather than behind. Great. So now we've got that, we just get to substitute back into these formulas here. Now it so happens that if you do this, you actually pretty much get 2 equivalent formulas, so I'm only going to do it for this first one here. Okay, so let's substitute that in and we're going to get... Okay, so now we've got that, the next step that we need to do is that we need to make an argument that all of these terms are either multiplied by sine of eta or cos of eta. Now we actually need this to hold true, that this entire expression equals 0 for all values of eta. So what that means is the only way that that can be true is if it's true when all the sine terms add up to 0 and all the cos terms add up to 0. That's the only way it can be true in general. So we can actually split this into 2 separate equations. One where we get all the coefficients in front of cos and they have to sum to 0, and then all of the coefficients in front of sine also have to sum to 0. So that's going to be our 2 equations. Let's start by doing the cos terms. So the first thing we get is rho double dot, then minus rho eta dot squared, minus gamma rho eta dot plus beta rho. And that's 1, 2, 3, 4. That's all of the terms. So excellent, that has to equal 0. Now, what I'm going to do with that one is I'm just going to actually simplify it, or when I say simplify, I mean factorize, and so I'm going to put all the rho terms together. Okay, now we're going to do this for sine. So, here we've got 3 terms, and because they've all got negative signs, I'm just going to cancel out those negatives in advance, so that means we get... Okay, and that was for sine. Okay, now the next argument that I need to make is I'm going to try and convince you that this term here has to equal 0. Now, the reason why this has to be 0 is it is actually possible that we could start with no angular velocity, or we could actually start with no velocity at all. So in that case, that means that our rho dot would be 0, and we'd have this rho dot eta dot all is 0 if we started with no velocity. But we still need this equation to be true. It has to hold for all circumstances. And in that case, if we had any sort of angular acceleration here that was non-zero and position that was non-zero, then we could actually have that this equation doesn't add to 0. So using that logic, we can actually get rid of this middle term here. And so that means that we can simplify our equation to... Now, it's impossible to guarantee that rho dot will actually be 0 here. So in that case, we know that this part here is actually what's going to have to equal 0. And so, therefore, we know that... Oh, whoops, I've missed a 2 here. Apologies, there's meant to be a 2 there. Then I can make that gamma over 2 is going to have to equal 0. Alright, so that's one equation. Now, if we have a look. Okay, now what they want us to do is they want us to find the form of eta. Now, we have a nice property here that we know that the double derivative of eta is 0, so we know that this is equal to 0, and we know that eta dot is equal to minus gamma over 2. So in this case, I guess we kind of know that we're going to have a polynomial in this particular case, so eta is just going to be, so in this case, minus gamma over 2t plus some sort of a constant. The constant's an angle. It's going to be, by the looks of it, the initial angle that we start in the circle. So I guess I'll just call it theta then. So if we just drew a quick little diagram of the scenario, this is the table, and here we've got a y-axis and an x-axis. So if we have a look, the way that they've defined x up the top here means that if theta equals 0, we're pointing in the x direction, so that means that this could be our initial position here. And then if we move around to, let's say, here, then this angle there, that's going to be our theta. And so I guess it makes more sense to call this theta naught. Alright, that's the functional form of eta. Alright, and now the next thing that they want us to do is to express the coefficient beta prime. So if we have a look here, this chunk of equation here, this is like beta prime. It's essentially just like the beta that we have here, except now that we've kind of changed our coordinates, we've managed to eliminate this kind of first derivative term. So that means we pretty much only have a beta term, and because it's the change of coordinates, rather than calling it beta, we're calling it beta prime. So this is going to be our beta prime. So I guess I can just write that out for us. Okay, and then from there we can actually substitute in our relationship up the top here for eta dot, and so that means that we're going to get our beta prime is equal to, okay, so we've now got our expression for beta prime, which is great, and then the last thing they want us to do, write down the condition for where we have different behavior with respect to our rho t. So this is all really coming down to this equation here. So I'm just going to rewrite it in terms of beta prime. Okay, so we've got this form of this equation here. Now what we want to do is consider what does this look like for different values of beta. So let's imagine for a minute that beta is positive. Okay, I've just realized I've made a sign error here, because if you have a look, I've got this as a negative beta here. So this should actually, so I've actually defined beta prime as the negative of this term here. I apologize for that. What that means is that this is actually going to be a plus here. Okay, sorry about that error. Let's keep going. So we've got, if beta prime is greater than 0, then if I was to bring this term to the other side, there'd be a minus sign in front of it. So I'll just write that out for us. So okay, and if you have a look, we've got the equation where we've got double derivative is equal to the negative of the term. So we already know that that's going to be a sinusoidal type function. So in that case, we know that we're going to get like sine and cos type answers, or in the word that we often call that is a harmonic function. So that means if we have beta greater than 0, this is going to be a harmonic function. Alright, now if beta is not negative, beta is positive, then this is clearly just going to be an exponential. So if you were to differentiate the term twice, you get itself plus this constant back. So it would just be the square root of that constant in the top part of your exponential, or in the power of your exponential. So if you have beta smaller than 0, then this is going to be exponential function. And then the interesting case, I guess, is when beta equals 0. In fact, this is probably the least interesting case. So in that case, we're just going to get a polynomial similar to the form that we had for eta up the top here. So now it's going to be the double derivative of O is going to be 0, and that just means that we're going to have a polynomial or a linear function of order, so polynomial degree 1. So I guess that we could just call this linear. Okay, and that's C3. Okay, so let's do C4. So in C4, they give us a range of initial conditions, and then they want us to use our solution from C3, and we're going to use that to find beta and gamma, and then we're going to find the corresponding value for capital omega, which can tell us how fast the table is rotating. First of all, let's have a look at these initial conditions. So they've given us that the initial position, I guess I may as well draw a diagram for this. Okay, then this is x and this is y. Alright, so we're starting at this initial position here, so that's going to be a distance of 1 meter away from the middle. Okay, and then we have velocity. No velocity in the our velocity in the x direction is 1 meter a second. Our velocity in the y direction is minus 1 meters a second. So that means the ball is going to be going this way. The interesting thing to note about that is that means that it's actually going the opposite way to the direction that we assumed that omega was going. So you might remember previously we were saying omega was this way. So in theory now we should actually get a negative value for omega. Let's find out when we get there. So from these initial conditions we can actually know a couple of things straight up. So first of all, if we wanted to know rho, how far away we were from the center at the start, we know that's going to be equal to 1. And we also know that our initial angle, I think I called it theta or theta naught before, but now I'm going to call it eta naught, that's going to be 0 from the diagram here, because we're starting in that x direction. Oh, sorry, I just realized that I drew that arrow in a slightly wrong direction because we have a positive initial velocity. We're actually going out in that direction. So apologies for that mistake there, but if we keep going, so because we have our initial position is in the x direction and our initial velocity has a component in the x direction of 1 meter a second, that means that we also know that the rate at which initially the distance from the center, rho, is increasing is 1 meter a second. Now we can also figure out what our initial eta dot is. This is actually a little bit tricky in my opinion to kind of think about, but the key thing that helps me realize this is just looking at the definition of x and y. So if we have a look, x of t, okay, and we might recall that we actually took the differential of this before as well, so I'll just quickly write up those differentials again. Okay, now if we substitute in time is equal to 0 and therefore eta is equal to 0, because of this condition that we have here, then I can actually see that first of all I recover the first equation is true because this last part goes away, but more usefully this part here, so this sign is going to be 0, that's going to go away, and then I already know that my rho is equal to 1. I know that my y, in this case they tell us, my y dot is minus 1 meter a second, and cos is just going to be equal to 1, so that means that eta is going to have to be to minus 1. Alright, so then when we do that, we can then use, we've got this equation from before, that we had that gamma plus 2 eta naught has to equal 0. So we have that from our differential equation. If you go back to B3, you'll remember I did something where it's like from sine and from cos, we get these two equations. This one came from our sine term once we established that the double derivative had to be 0. So this means that we can then get our gamma. So gamma is going to equal to 2. Now, to get our beta, what we can do is, luckily for us, we only have to examine the simplest case here. So we don't have to worry about the scenarios where beta prime was greater than or less than 0. We only have to worry about the case where beta prime is equal to 0. So in that case, from that condition, get that beta equals minus 1, and we also know that rho double dot is equal to 0. Now, once we have that information, we know that rho started at a value of 1. And we know that rho has a gradient of 1 and no acceleration. So that means we can actually just find the functional form of rho directly here. So in this case, it's just going to be 1 plus t. Now, we can also actually then find an equation for x and y. Because we know what eta is, we have our eta value from before. So before we found that eta was equal to this here, but since then we've actually found what gamma is, and we now know what eta naught is. So eta naught 0, so that goes away. And we know that gamma is equal to 2, which means that eta is simply minus t. So we can now substitute all of that into our expressions for x and y. Apologies that I didn't write up the y expression before, so I'll just put it up there now. So okay, so if we just substitute in our functions that we've got, so that's this one and this one, into those equations, then we get, and of course the cos of minus t is just equal to the cos of t, so that means we get, and the sine of minus t is equal to minus sine of t, so we get that. Okay, now at this point, I'll just point out, because they do this in the solutions, that this rho that we've got here is essentially equal to the capital R, the variable that we've been looking at before, or the scalar version of that. So that means that we can quickly verify, I guess this is true, by doing x squared plus y squared. We know it's going to equal to capital R squared, but it should also equal to 1 plus t squared, and we can see that that's true. So now what we need to do is, they want us to use these values for beta and gamma that we've found, and we want to use that to figure out capital omega is, and we've already got a bit of an idea that it might be negative because it's the opposite direction to what we thought originally. And then they want us to be able to determine the sign of Q, so is the charge here positive or negative? Alright, so in order to be able to find omega and Q, what I'm first going to do is take our definitions of beta and gamma, so that's the two that we've got at the top here, and I'm going to set them equal to their respective values. So we have, okay, and we actually also know that the moment of inertia of this ball is mr squared over 10. Okay, so let's substitute that in. So first, let's start with our beta term. So if I just add mr squared to my I in this case, I'm just going to get 11 over 10 mr squared. Alright, and I can cancel out my r squared values here. Alright, and then just a little bit of rearranging leaves me with, now let's deal with the gamma term. So from gamma I have, okay, and then once again we can substitute for I, in which case we're going to get, okay, now I'm going to cancel that mr squared on the top and the bottom, so this goes away, I get a factor of m on the bottom, and that r squared goes away. Then I'm also going to multiply the top and bottom of this fraction by 10, which means that I'm going to get 40, and then those 1 over 10s are going to cancel out. And then I'm going to multiply both sides by 11 to get rid of my denominator. And now what I want to do, just to simplify things a little bit, is I'm going to call this a. So that means that this here is just equal to 4a. And so that means I can rewrite my equation on the left hand side here. That's going to be a omega equals minus 11, and this one here is going to be 4a minus omega equals 22. Alright, so from this equation on this side I can get that a is equal to minus 11 over omega, and I can substitute that into my right hand side, so then I get 44 over omega minus 44 over omega minus omega equals 22. Alright, so let's rearrange the equation now, in which case we're going to get, okay, and then we can use the reduced quadratic formula, which is going to give us, which then gives us, alrighty, and we have our answer. Now the key thing to notice is 11 is greater than the square root of 77, so that means that omega is always going to be negative. So that means that for both of these speeds, omega does spin in the opposite direction, so not the direction shown here, but it actually spins in the minus z direction. Okay, now we can actually use this to try and figure out what Q is. So let's go back and substitute for our A. Okay, so we've got A is equal to all of this, and that's equal to minus 11 over omega, and omega is negative. So that means all of this is positive. B was in the positive z direction, and m, the mass, also has to be positive. So according to this logic, I would say that Q has to be positive in this scenario. So once again, I disagree with the solutions. I think that Q has to be greater than 0 in this scenario. Otherwise, this equation can't be true. Alright, and with that, let's have a look at C5. Alrighty guys, so for C5, I'll just do a quick diagram of what our trajectory looks like. Essentially, the ball is going to start somewhere here, and then it's just going to start to spiral outwards, and it's clearly one of the things that we know is that the value for eta, so that's essentially what the angular velocity is not changing with time. So essentially, like our eta dot here is just equal to 1, some constant. And so what that means is that we're going to actually have a cycle go around with a timing of 2 pi. So the period of one cycle is 2 pi in seconds. Now, at this point, I'm just going to say for this part of the problem, we kind of start to leave normal physics a little bit. We just get to throw everything away pretty much. They don't want us to care about units anymore. They don't want us to care about actually using numbers. They've pretty much just set everything to 1. For some weird reason, they've set the moment of inertia to 1 over 11, which is inconsistent with the formula they've given before, but we'll just go with it. And so you can't really dimension check. The other thing to notice is they're telling us that when the number of cycles is very, very large. So essentially this spiral is going to get very, very big. The object is going to be moving very, very fast when it gets far away from the center. The exact initial position you can pretty much ignore, and same for the initial velocity. So what I might just point out that is if the ball is going to get further and further away, but it needs to keep up the same angular velocity, then the velocity is going to get very, very fast. So in this particular case, we can actually pretty much just say that the velocity, so that's r dot or v, is essentially equal to 2 pi times the cycle in our new dimensionless world, so times the cycle number, and in our new dimensionless world, that's also pretty much the radius of the circle. So this one, the velocity is in meters per second, and this one's in meters, but yeah, it doesn't really matter too much. We get to be super casual with units and everything in this part. Alright, so now for the total amount of energy, what they've written looks very complicated, but really this system has got energy. There's 2 types. There's rotational energy and there's the normal kinetic energy. So the rotational energy is equal to I, and then it would be omega squared, except there is a correction term that we're going to have to put into place because we haven't taken into account that the table is spinning. But otherwise it's just the normal I omega squared, and then the kinetic energy is mv squared. Now v is just this 2 pi n, and m is just 1. So this bit here becomes super easy to deal with. The only part of this that becomes a little bit complicated is when we want to deal with the fact that the table is actually spinning. Then that's going to affect the ball omega, how fast it actually has to rotate. So to take that one into account, what we're going to have to do, we're going to use the no slip condition, and so in the solutions they actually just give us a form of it, which is very convenient. So I'm just going to take it, omega squared equals v squared plus omega r both squared plus the cross term. So in this case it's 2 omega v dot z cross r. Now they make a very valid argument in the solutions that once you're very far away from the center, so if you're a long way out on one of these spirals, then essentially v and r are orthogonal to each other. So what that means is that when you take this dot product with this cross product, you're essentially just going to get v multiplied by r. So like this, and then they make note that this can just be factorized like this. Okay, so now and they've told us that they want us to use I equals 1 over 11. So in this expression here, now we've got, okay, in v is just 2 pi n plus omega times r, which is 2 pi n. That's all squared. And then we've still got our second term, so we've still got this term. So plus m equals 1, and v is 2 pi n squared. So if we put all that together, we can factorize out the 4 pi squared n squared. Sorry, I just realized I did a bad thing. You guys are going to get me in a lot of trouble for this. Of course it's half I omega squared and half mv squared, so all this is multiplied by a half. So this is actually 2 pi squared, not 4 pi squared. Apologies. Alright, and then what I'm going to do here is assume that like everything except for n squared is essentially like a constant now. So we just want to know what's the difference between, so this is like the total energy at the moment. We want to know what's the change in energy from one to the other. So if you like, what's the change in energy? That's if we were going to go from like the nth total energy and subtract off the n minus 1 total energy. So to do that, essentially this is just coming down to subtracting a quadratic. So we have like capital N squared, and we want to essentially subtract off n minus 1 squared from that. So if we do this, our n squared terms are going to cancel out here, and that means that we're just going to get plus 2n and minus 1. Now when n is very large, we can ignore the 1, so this is just going to be equal to 2n. So that means that we just have to double like this expression in here, and so we get 4 pi squared n 1 plus omega over 11 plus 1, this is squared. And that's going to be the change in energy for one cycle. Now the version of the solutions that I've got doesn't have pi squared, it's just got 4, but I believe that that's an error. Alright, and that is a very long and difficult problem over. I hope that you guys have found this helpful. If you found any errors, please let me know and I can update the video. Thank you very much.